right, success. Okay, so we just did a couple of problems. I think it was, I don't know, up to 12-3. All right. And so just making a note of that. So now let's go ahead and look at page 102 for question 12.4. And I'll bring it up on screen. Whoops, where are we here? So this is a lot more fun when we're in class, but we actually have this demo. So it actually explains why you should not bend at the knees, or why you should bend at the knees when you're picking up heavy objects, why you should. And this is a very crude model of the human body. So just kind of guiding you through it, this causes, you hang a dumbbell here and this causes a torque, which is equivalent to the head, the torso, and the arms, all that weight. So when you bend over, your body, right, you've got your head and your chest and your arms exerting a huge torque. Now, this is assuming you bend over perfectly. And now a weird thing that happens here, the muscles from your spine connect at this weird angle right here. All right, so that approximately, now if you know anything about biology, it's actually a whole bunch of different muscles, but on average, we're going to say these muscles form one giant fiber approximately with these at this connection point with this angle. In practice, it's much more complicated than that. But think about this right now. You could probably see this. You've got a huge lever arm and a huge force, right, from your chest and all that body. Like think maybe 50 to 80 pounds or something, right? Crazy. So, all right, great. And now, and right here, the mass that I'm using is kind of like for a little child. So this would be for a child. You might have 20 kilograms, say, all right, 4 times as much. And then because this is such a small angle, and because torque is R F sine of 12 degrees, you have a small r, you have a small angle, this force on your lower back is insane. Insane. Okay? So, blah, 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 blah. Oh, so we could figure out this torque and do all this crap. So to be clear, if you're curious how much a normal person is, this is the torque. And I'm going to go look at the solution really quick. So notice it's about 3 times. So it's scaled off by a factor of 3. So this is one third of a medium adult. So notice for you guys, when you bend over like this, you expect 400 pounds of force on your lower back muscles just from bending over and not lifting anything, just from holding yourself in static equilibrium. If you bend over, this is why people throw out their back if you try to lift anything. Because if you lift anything, it's going to put a dramatic increase in this. A dramatic increase in this goes right through to there, and you get this huge force on you. So that's why you bend your knees. All right, let's leave it at that. I'll check the chat real quick. On the word web search. Okay, thank you. Is that in the solution?
In the workbook.
Oh, in the workbook itself. Okay, so all right, I'll fix that up. Okay. Okay, I got you. I see it. Problem statement. Thank you. Oh no, I meant Reb Sarach. Don't you know? Yeah. Okay, good. Thanks, Trey. Okay, so let's go to the next one. All right. And right now, what I'd like to do is kind of pick up the pace, and I'd like to talk about the free body diagrams, because once you get to algebra, you're pretty good. So actually, before I start doing that, I just want to confirm you're all okay with that. So I'd like to spend a lot of time talking about the free body diagrams, maybe the torque equations, and then leave the rest for you. Is everybody cool with that? So we can get, yep, I see one response. Just kind of give me a heads up. Tell me what you're thinking. All right, that looks like the plan. All right, let's go for it. And that will reduce the effort when you need to do these problems. So let's look at the next one. Okay, a ladder. So in this case, we've got a ladder here leaning up against coefficient of friction. And notice it doesn't say anything here, but let's assume, oh, I see. Eventually, somewhere in here, it says, what is the minimum coefficient to keep it from sliding? So this tells me, aha, this is the case where it will be, oh, I see. Okay, so look, there's two cases. Part C is it's not on the verge of slipping. And part D says, what is it if it is on the verge of slipping? Okay, so take a second and draw the forces. And remember, I'm just getting the picture bigger. Draw the forces on the ladder. And I think it says negligible friction up here on the wall. So up here, you can assume mu equals 0. No friction, okay? All right, so draw the forces which you think, and then I'll draw them as well. So don't look at the screen while I'm drawing, all right? All right, and so hopefully you drew this FBD, everybody. I don't know why my screen's got this one right here, but whatever, whoops. There we go. Now it looks a little better. You have a normal force from the floor, you have friction from the floor, you have mg, whoops, that's supposed to be in green, and you have a normal force from the wall. You might be saying, why is there no friction? Remember, we said that there was negligible friction up there. So that's why normally you would actually have friction pointing up. So to be clear, it's possible you could have an upwards friction here that's helping to hold the ladder up, but this problem specifically said there was no friction with the wall. So that's the only change if there was friction with the wall. And then from here, if you were trying to learn about this problem, there's 3 obvious pivot points. The 3 obvious pivot points are right here, and right here. So the red dot, green dot, and blue dot are the obvious choices of pivot point. For me, the obvious one to start with is the red dot. I would choose the red dot because that gets rid of 2 forces and it makes an easier torque equation. All right. Once I get the red dot, I would not do another torque equation. I would only do torques about the red dot. And then think about this, everybody. Think. I want you to think for a second with me. Normally, in this problem, we're going to know the length and the mass. How many things are unknown? How many forces are unknown? Think. How many forces are unknown? Hopefully you said 3. If you have 3 unknown forces, how many equations do you need? Think. You're going to do, whoops. Sum of torques about the red dot equals 0. I could do sum of forces in the X equals 0. And then finally, I could do sum of forces in the Y. So for this problem, you only need to do one sum of torque equation. So again, with static equilibrium, we have these 2 equations, the last 2, and then if you have more unknowns, you can start adding in more and more torque equations. Usually, this is the easiest to start with because it eliminates 2 unknowns and it gets normal force of the wall right away. Okay, so that's the kind of big picture. Let's go look at the solution and see if there's anything I left out. Okay. So in this case, here's sum of forces. I should probably label those, huh? So that first one is sum of forces in the y direction. This is 12.5 E. And this is sum of forces in the x direction. This is sum of torques. Notice what I did here. I cheated. I said the negatives equal the positives, or you could say the positives equal the negatives. So this right here according to the coordinate system I chose, that is going to be a negative torque, right? Whereas the other one is going to be a, whoops, sorry, I misspoke. N2 causes a negative torque, and mg causes a positive torque. And what I did is I just said the pluses equal the minuses. And again, this is the magnitude of the negative, and this is the magnitude of the positive torque. So the magnitude of the positive torques equals the magnitudes of the negative torques. Here, it's just like the ups equal the downs, ups equal the downs. It's the same kind of thing. Obviously, up has a positive j hat and down has a negative j hat, but these are the magnitudes of the ups and downs. Is that clear, everybody? If so, hopefully yes. If not, add a question in the chat. I don't normally tell you to memorize trig identities, but this is huge. You got to memorize this, people. Make a note, memorize this, okay? You're going to get an equation sheet for your final, just like on the test 2, so that you can have good speed. So I'll let you write 1 page, 8.5 by 11 for your final exam. Put this on there or memorize it, okay? You got to know this. Okay, so in part C, we're not at the onset of slipping. You rearrange that, you get this equation. Make sure you can do that. If it is at the onset of slipping, we get this unusual result because F1 is mu static N1, but N1 is mg, so the mg's cancel out and you get this cool result. All right, let's call that good. All right, still good. Let's go on to the next one. Take a look at the next one. 12.6. It's very similar, only now I've added an extra person on here. And this is the fun part, okay? If you step on the ladder, is it more likely or less likely to slip? In particular, if it's on the verge of slipping and then you step on it, is it going to slide out on you or is it not? That's my question. Just think about it for a second. If you step on the ladder when it's on the verge of slipping, would it be more likely to slip or less likely to slip? When you step on it, are you going to crash and get hurt? I'll let you think for a minute. You could discuss with your neighbor whatever you want via separate chat or something. I have no idea how you would do that. But... And now I'll go to the solution. This is a lot more fun to do in class with a real ladder because I actually do this one. I built a little mini ladder. It turns out when you step on the ladder, it's less likely to slip. However, as you go up and up and up, once you pass the center of mass, it will slip. So this is really dangerous. When you first step on a ladder, it feels extra secure because you're putting more weight. You're right. Think about it. When you put the weight right here, this normal force gets bigger. So the maximum possible value of friction goes up and you're safer. But as you go towards the other end, oh crap. When you get up here, you're just, the normal force is still going to go up, but you're exerting more of a torque and there's not enough friction to balance that torque. And so as that happens, you could actually feel safer until you get past halfway. Then you're really high up on the ladder and then you get killed. So that's dangerous. So let me clear that out. So make sure the ladder is not about to slip. That's the moral of the story. Sometimes what you could do is if you're really serious, sometimes you could put a rope here and tie it to the wall. But in general, just use a very slight angle, the slightest angle possible that actually works for the building that you're on. Okay. Yeah, let's go look at the solution and see, all right? So when you do this one, the forces don't change. You basically double you do get a bigger normal force, right? And so you'll get this frictional force is, let's see, still equal to N2. And so that's what's interesting here. You cannot jack up this friction force, but you can jack up the maximum possible frictional force. Now, so if you have extra weight on the bottom step, it's less likely to slip. But what I was trying to say here is as you go up and up and up, this becomes an issue right here. Okay. So as this goes up and up and up, that's D gets bigger and bigger because you're going farther and farther up the ladder. And so notice I used lever arms here. These are lever arms. I guess I should make sure that makes sense to you. So everybody take a second and see how this works. A lot of these problems I'm going to start doing with lever arms. Let's take a second and make sure. I want to analyze this torque equation because that's the new bit. And I want you to see how I got it. Okay. So what I did here, if I could, this force uses this lever arm. So I said the force times R perpendicular. This is R perpendicular to this red force here. So notice that's this one, mg, and this part is R perpendicular. And now for this other one, this is R perpendicular. Do you see that? This is the perpendicular for that other force. So all of that garbage right there is R perpendicular to this force right here. So I want to pause and make sure everybody is okay, because if you can't get the torque equation, you're screwed. All right. You really have to be able to get that. So much of these on test, the final exam is going to rely on getting the torque equation because that's the first piece of the puzzle. So I don't care how good you are at chapter 5 and 6, you're worthless in chapter 12 if you can't do the perpendicular lever arm crap. So yeah, because the first, usually part A of this question on the test, you have to get the lever arm right or the torque. Okay. Yes, this is with the pivot at the bottom. Thank you for pointing that out. So the pivot point is right here. Yep, yep. All right. I'm going to hope you're doing all right. Okay. So let's check. That's cool. Let's take a look at 12.7, everybody. 12.7, the next one. All right. So we've got, if we can get to 12.7 and 8, that's pretty good here. So let's take a look at that. Okay. 12.7. Again, we got to focus on the FBDs. All right. And my apologies if I'm going too fast now, but yeah. All right. So with this one, I'm just going to give you another picture of this one. It's a drawbridge. Whoops. Oh, jeez. That's better than on my crotch, I guess. There we go. Better be careful here. So it's this scenario right here. Instead of being horizontal, it's like this. So it's a drawbridge. And so the stapler is like the person on the horse. This string is the cable. So what's going to happen now if you have a downward angled thing? This is a classic problem to deal with, all right? So let's go look at it. All right, hopefully that visualization made some sense. Draw the forces, see if you could beat me to it, okay? And remember, you might need a separate picture for all the angles, but at least get the forces drawn. Forget about doing the problem in order. Draw the forces. It's going to be some tension. Going to be a 2mg. If I had to guess from this problem for the reaction force, I would guess it's probably to the right and up. I'm just guessing. And it looks like it might have, I don't know. I'm just going to guess. I have no idea. If I'm wrong, that'll come out in the math, okay? Did I forget any forces? The mass of the rod itself. So hopefully that's what you thought. Yep, good job. And I should be careful. I said mass of the rod, and mass is not a force. So both Nate Dogg and I, we should say weight. Yep, you're right, Jay. Okay, good job. Okay, so there we go. So now we've got our forces. Look at how complicated this picture is getting. How am I supposed to analyze the angles with all these arrows and lines on it? It looks like crap. This is why I tell you to draw one picture for the angles, one for the forces for your torque diagram, and then another for there. Now, I want to point out the torque diagram looks like this. If I was going to split these into components, let me do this. It's very complicated if you want to do torque. So please pay attention, everybody, right now. This is the force perpendicular if I'm doing torque, and this is the force parallel. Notice this is not tension subscript Y. It's not going straight up. That is wrong. Okay? This is tension perpendicular, and this is tension parallel to the rod. They are not X and Y. Now, if I was going to try and do, give me just a second. If I was going to try and do the force equations, this is the main difference. That is tension in the Y direction. So if I'm doing a force diagram, I need to use these. And notice the X is also different. So notice there's a difference between force perpendicular and force in the Y direction. Force perpendicular means force perpendicular to the rod. Not necessarily the same thing. And so guess what type of question you're more likely to get on a test? This. Because it tests if you could tell the difference between forces for torques and forces for a free body diagram. For force equations. Now, this is messy. I'm going to go ahead and look at the solution really quick and see what I expect for you, what I want you to know how to do, okay? We have one picture for the angles and lengths. This is the one we started with today. Notice this helps me figure out all kinds of stuff. Look at this clever trick. I took a triangle which is not a right triangle and made it into a right triangle by being clever. Look at this. You take a triangle which is not right triangle, in this case an obtuse triangle, and I change it into a right triangle by doing some geometry. This is a very important trick for a physics class, okay? Then I have my forces drawn this way, and it looks like I probably could have drawn this one down here, but it was starting to overlap, so whatever, okay? Take a second to look at the solution, and let's see if this makes sense here. Let's read the question. I forgot the question. So let's do that again. All right, so there was the question. Use geometry to prove this crap. Okay, and notice this angle was given, and Y is given in terms of L. All right. And so let's look at parts A, B, and C in the solution and see if we understand them. Number one is figure out all the angles, alpha and beta. Number two is FBD. We kind of did that. And then make sure you can write down the sum of forces and torques. So let's look at part A and C in the solution. Part A. Okay, this was theta. That makes this 180 minus theta. I think that's easy to see, but let's confirm you're okay with that. So if this is theta, this is 180 minus theta. And so I can label it. I need to get even bigger. Sorry. Now, if you want, hopefully you agree that this angle down here is 90 minus theta. And to be careful, I should stick a degree symbol on there. So 90 minus theta there. Everybody good? Hopefully. So now take a look. This side is going to be L cosine because it's adjacent to theta. This side gets the cosine. It's adjacent. That means this side gets the sine. We'll take a look. If I know this side and this side and this side in terms of L, and remember, theta is a given. Theta is 85 degrees. That makes this, what is it going to be? 95 degrees if I did the math right in my head. Hopefully I didn't screw that up. Okay. And so we know those two angles. We can actually figure this out. I know that this angle down here is going to be 5 degrees. So I know that beta plus 5 is this whole angle. Like I said, this angle right here is beta plus 5. And this is the kind of stuff you end up spending a lot of time on in chapter 12, geometry. Okay. So in this case, I could now do tangent of beta plus 5. And this might be slightly different than what I did in the solutions, but it gives you an idea of the kind of tricks you can do. If I did tangent of beta plus 5, that's going to equal this over that, right? And I just wanted to show you something here. Sorry, it's taken so long. So notice this would help me figure out this angle, because notice L drops out. Every term has an L. L drops out. I know this number. I know this number. I could take inverse tangent. Once I get inverse tangent, I got this. Notice this equation right here is very similar, but I did the other angle. Tangent of theta, or sorry, tangent of alpha is opposite over adjacent. That's what gives me this equation. And so you can figure out alpha and beta. A cool trick, we could say that this angle right here plus this angle right here plus this angle right here, alpha plus beta plus 180 minus theta adds up to 180. And so if you get one of these, if you get alpha, you could use the triangle angles. They sum to 180. And I'm going to zoom out so we can see all this crap. Use the fact that the angles there and figure not to scale. So it's really hard to draw this one to scale, so I didn't. So that's the angles for part A. I'm going to pause. Any questions on part A? And you could, I hope you notice there's a lot of different ways you could do it. Maybe you had a different way that came to your mind. That's totally fine. Some people might use like some parallel line theorems, like the alternate interior angles. So this angle and this angle up here are related by some parallel lines. Some people do it that way. You might use a different, I don't know, exterior angles or something. So, but geometry is crucial.
I have a quick question.
Yeah, go for it.
Since you kind of made like a second triangle there, do you think there'd be a way to like solve for one in terms of the other and plug it into another equation? Like if you have two equations for alpha and beta?
Oh, maybe that might be possible too. Okay. But I do know from experience what I have found that makes these problems doable in a timely manner is that trick of turning the oblique triangle into a right triangle. So again, just to clarify and make sure I made clear, it's this trick right here where what I did is I took this non-right triangle and I figured out how to make it into a right triangle because I'm good with right triangles. And now you might recall that Alexis was talking earlier about the law of sines and cosines. I bet you could do that problem faster with the law of sines and cosines, but I'm just such a right triangle kind of guy that I'm like, you know what? I'm just going to go right triangle all the way. So this is probably a problem where you could do better by using law of sines or cosines. Please, I'm teaching in class, all right? All right, sorry, I got distracted there. Let's get back into it. All right. Yeah. Question? Did I answer your question, Ryan?
Yeah, that's good. That makes sense. Yeah.
Okay. So
yeah, I hate law of cosines and sines.
yeah, and they're fine. Sometimes they're really useful. It's just I have a limited brain capacity, and so that's one of the things I chose to forget because I'm good with right triangles.
Yeah.
All right. Good. All right, and so let's check the torque equation and move on. Oh, sheesh, it's time to go. Okay, I'm gonna let you do the torque equation. I want to show you one last thing before we go, everybody. So I just want to make sure you understand circles because we haven't done circles. And then next time we can pick up after this. So we could pick up that problem again, or you could do the rest on your own. We did the FBD already. I want to talk about this one. And because we're running out of time, I'm going to stop yakking and get right to it. So I'm looking at 12.8. And I'm most concerned with the free body diagram, okay? So if you have circles, this is what I want you to understand. There's going to be a force on the ball this way, towards the center. There's going to be a force on the ball from the wall towards the center. Now, in this case, there might also be friction. So there's probably some friction holding this ball up with the wall. And maybe there's some friction over here. And I'm just going to guess that there's friction going this way. Why? Well, the friction at point A is trying to rotate the ball. So I need friction at point B to oppose that rotation. Otherwise, the ball is going to slip out. All right. And so these are the forces on the ball. Check this. By Newton's third law, I know there's a force this way and this way corresponding to these two forces. So to be clear, the green arrows act on the plank. The orange arrows act on the ball. And so they're related by Newton's third law. Now, obviously, there's the weight of the ball itself. Can't see that very well. It's a little better. The color's kind of crappy. There we go. So there's the weight of the ball itself, and then there's also the weight of the plank. So, and if I was doing this, I'd have to be careful. There's probably going to be a reaction force at the pivot. So I'm just going to pause for a second. There's going to be a reaction force at the pivot, and I can't quite fit it in because my diagram's not going to do it. But I will say this, I'm going to try and do it. There's going to be a reaction force at the pivot. Oh, I can't. Okay, so let me move this down here, and I'm going to annotate. There's going to be a reaction force at the pivot going this way and then also up. And hopefully you could see that all right. So there's going to be a lot of different forces, and we see that there, I could move that thing finally. Notice that these this force, the green force, and this blue force all act on the plank, whereas these forces and this orange force all act on the ball. So you got to be careful when you do these. And to be honest, I could care less if you could solve this problem, but I am interested in you drawing the FBDs, getting the force equations right, and getting the torque equations right. So that's what's going to matter most to you in doing these problems. We're going to pick up here next time. I'm going to stop the